Thanks, Peter and Brian. And remember that both of them will join us at the end of this next presentation for our roundtable discussion and Q&A. So next up is another technology-focused presentation. This one's on the optical metrology and using the data in real time to improve metal forming processes on the press room floor. Our speaker is Yanni Psilopoulos. He's the technical account manager at Trillion Quality Systems. Yanni has more than 20 years of experience in the tool and die and manufacturing arena. And today his focus is on helping metal formers better understand panel formability and achieving cost savings by using optical metrology technology within an Industry 4.0 platform. Please welcome Yanni.
Well, thank you for that introduction. And I appreciate being here. My name is Yanni Psilopoulos from Trillion Quality Systems. Again, I'm the technical account manager at Trillion Quality Systems, and I've been assisting customers performing or installing these technologies and these solutions for Industry 4.0 formability. And we're just going to go through how these different technologies assist and can go through to help your companies get better data quicker and be part of Internet of Things. So Trillion Quality Systems is based in King of Prussia, Pennsylvania. This is our office. We offer many different services, like engineering services. These are meetings and customer trainings. On top of that, but we do a lot of different things with the technology, but today we're going to talk about a few different areas. First, we're going to talk about DIC for material properties, bulge testing, Nakajima testing for incoming inspections, and the benefits of knowing all that information coming in. From there, we're going to move into optical forming analysis, OFA patterning, the difference of chemical etching versus laser etching and the benefits of laser etching and robotic laser etching and what that can afford your facility and the available data that will give you. And then optical forming analysis, the measurement itself, how attaining the full field knowledge of a panel for formability is very beneficial. And then the last step we're going to go through is using DIC, digital image correlation, for press deflection and really understanding your machinery's behavior during the manufacturing or formability process. Going into the metrology side, the whole formability 4.0 metrology side is, again, we're going to be going through incoming material for producing FLCs or forming limit curves, understanding laser etching, and being able to put a precise pattern down on your part to be able to get less noise and better data. And then using the OFA or the optical forming analysis to see the full panel's result of the forming process and really being able to track down problems, and then going into the full automated version of OFA in a type of robotic cell that's out there in the industry for everyone to use. And then again, using our technology to use DIC for press deflection to understand and put the whole picture together to make sure that everything is working the way it should be. So first, we're going to start with tensile testing and its importance of understanding the incoming material, getting good end values, and understanding nonlinear forming. DIC for material testing will give you, as in this picture here, you'll see that there is a full field response of the actual sample. Instead of one strain gauge, we're using thousands and thousands of strain gauges to really understand the behavior of the part. Here's a nice video understanding how the material is separating and pulling apart during a tensile test to really understand its behavior and its makeup from rolling direction per each lot of steel. But you can determine the material's parameters of any material, the strain distribution, and to analyze local areas during this process. As I mentioned, what DIC affords you is the ability of not just using one strain gauge in one location, is the ability of having the full field response or knowledge of what the sample is doing. With that image acquisition, you're able to get automated image processing, which gives you the 3D measurement of the data set, which will automatically map the Young's modulus, the Poisson's ratio, the R and the N value onto a graph automatically with not having to go back and do it yourself at one location and missing the actual event. This is the important part of DIC. With that, you can perform, as I mentioned, Nakajima test and bulge testing for each material that's incoming to really understand, is that material what you ordered? Is it been sitting outside? Is it past its expiration date? Things like that. but using DIC to get your uniaxial strain condition, your plane strain condition at number 2 here in the middle of the screen, and then the biaxial on the far right side. This is crucial because even though the N values are stated as being the same of materials, knowing this as they come in could save you a ton of time, downtime in your press, and understanding what the material is doing as you move forward. Here's a nice video explaining how our quote-unquote kiosk mode or automated version of using DIC can serve the purpose of being able to just plug and play, putting the sample in and hitting go, and you see the response of the structure live in real time. And then these are all capable of being uploaded to a database that can be accessed by anybody, anywhere, for current testing happening, so they can understand what is a specific lot of steel if there is something happening down the line. You'll also notice here that they're automatically graphed. This can be part of the report with some inputs from the user itself. Everything else is automated, and these can be saved using our parametric ability, so that the operator just needs to put the material in the machine and hit the go button, and the test is happening automatically. So there's really low manual power needed as far as an employee to be doing this over and over again. It's just hitting a button and putting the sample in. So the importance of it, as I mentioned, DIC for automated incoming inspection is performing the material test and getting the full knowledge of that sample, and then using the parametric templates for easy repeated testing. Corrected FLC, so you're getting the right FLC for that lot of steel. We see a lot of that as the material should be the same, but maybe it isn't, and you're not getting the results of the actual material being used. And then understanding better the N value and the nonlinear forming, as DIC gives you the capability of shooting at a higher frequency to really understand what's it doing from point A to point B as it's actually forming, whether in the Nakajima test or in the tensile test. So what is the outcome here is understanding it. Its fulfilled response is reducing tool changes, reducing the press downtime, and leading to a better product quality, which leads to higher production output and less dedicated resources. How does this all connect, as we mentioned, to Industry 4.0? It allows the operator to do things more automatically, from the reporting to the sharing of this information, but really understanding what each lot of steel is doing quickly and efficiently. The parametrics allow you to build a library for each sample of material and then just pull that up and hit go. And that's using our automated kiosk mode. So it's a very nice feature of DIC to have that ability to do that for each incoming material, for each facility, as opposed to relying on a testing house outside to just do it for themselves. I mean, they can do it for themselves. Now we're going to move into the sheet metal etching of optical forming analysis. Currently, chemical etching is the standard. It's very hazardous from the chemical standpoint. It's variable accuracy. So from etch to etch, depending on who's doing it, you might get a higher noise level, and it's not going to be very uniform because of how they do that. So laser marking is a precise way to go, and it's very automated. You're always going to get the same noise level and the better pattern for each one. So the measuring principle here is that the computation of 3D points on all dots in at least 3 camera positions, using it for OFA, but being able to have that nice pattern on the part will give you the best result for your 3D coordinates, your major and minor strain, and your material thickness. It'll give you a better forming limit diagram, or as it relates to the forming limit diagram, because as you're near the failing point, you want to know exactly how close you are to be able to share with the toolmaker. You can also validate and optimize numerical models more accurately, because now you're closer to that zero reference, or that perfect world that FEM is allowing you to do. The aim of the solution of laser etching for OFA would be to autonomously create the laser etch, which takes the manpower completely out of it, is allowing the unit to do the job repeatedly without wasting material and wasting time, but allowing that same person to do other jobs at the same time. The expected results, again, would be to get a perfectly etched dot pattern with low noise repeatedly on every sample, and being able to just set it and forget it. Here are some examples of laser etching for OFA. You see the noise level here in the X direction and the Y direction. gives you very low noise, plus or minus 0.2%. On a very expedient way of etching. It roughly takes 6 minutes per grid, 6.5 minutes per grid. That you can see is very close to zero as opposed to what we see with chemical etching. So it's a lot more accurate, a lot more repeatable. So again, you're not wasting material. So looking here at the results here, this is a panel that past the bead on this type of panel would have been wiped away, where the laser etching survived, because we can manipulate the intensity of the burn on the laser and get better results across more difficult parts than what we can on chemical etching. So again, less time doing the same type of measurement and getting better data across the board to build that database of understanding what previous results have given you to make better decisions moving forward. So this is just a quick breakdown of a laser etching robot and what the cost savings would be. I don't want to go through each and every one of these, but understanding that it is a cost savings, less man hours, it's more accurate, and it reduces downtime splits because you're getting that more accurate read to understand what's happening, as opposed to being that 1% off from chemical etching. You're getting that closer to 0.2%, closer to zero on a consistent basis to get a better results. So moving into how it connects again to the Industry 4.0 is that allows you to create a repeatable pattern for OFA. The patterns have the least amount of noise for better accuracy. And it is that set it and forget it mentality where the operator can literally just put it down, hit a button, walk away, and do other things like the actual OFA measurement, and being able to move forward with doing more things and getting the perfect panel without worrying about, is it going to be a lot of noise, or am I going to get a good panel to read in a couple of hours once it gets hit. The other cool thing about it is that you can build a library of patterns for each material with their settings. So each time you don't have to worry about, is this chemical correct? Is this recipe of chemicals correct to get a good pattern? You just pull up that program and run it for that particular pattern, and it runs each time. So it's a very low downtime, constant workability for on-the-clock operations. Going into the actual optical forming analysis itself is basically automating the circle grid analysis process. Looking at the process itself, you'll see here that the operator is using, in this case, a single DSLR camera, taking images from different heights and then rotating it. And while the images are being automatically transmitted to the software, the measurement is automatically being taken place, where before you would have to look at circle grid analysis, one circle at a time with a Mylar and a magnifying glass to figure out what direction everything is going, the major and minor strain, things like that. This is just all automated by just taking some high resolution images very quickly. You'll see here again, it's wireless, so it's transmitting the images fast. Going into the results side of the OFA, you'll see after all the images are automatically computed, the result on screen looks very similar to a finite element model. The difference is that this is the actual result of the forming process. So you're looking at major strain very quickly and easily. The operator can go to different strains like minor strain or thickness reduction. Everything has been calculated. So now you see the full parts response to whatever forming station you're looking for, whether it be the draw station, the restrike station, the pierce station. You can actually track this throughout every forming ability. And you see here some of the results that are available to the user to check whether it's displacement Z's, epsilon X or Y, things like that. Some of the applications that you can use this for is the monitoring of process stability in a series production. This is important because you can bring in the FEA data and then also track it through a series run. So again, you're going to bring in the 3D coordinate of the 3D model of the FEA data, perform what's called a best fit of the panel, calculate the surface geometry deviations similar to what you would see in a blue light scanner for dimensional differences. Then the system offers the ability, or these systems offer the ability to do a direct overlay of the two samples. And then as the user has full control over that alignment, we'll map those results in those locations to see, are we one-to-one? Are we good major strain to major strain, minor to minor, and things like that. But as you see here, it calculates the differences between FEA and the actual measurement at the bottom, where you see the green and the blue in that bottom measurement, to see where the differences are. And those are hard numbers, not just colors. Those are hard numbers that you can pick and really understand the part's behavior. So the simulation verification offers the ability of verification of boundary conditions, the knowledge building of the different transfers, and the optimization of the simulation process. So your part might be safe, your actual part might be safe, but it might not be matching FEA or vice versa. In this case, you can report that back upstream and then feed that data back to be more proactive as opposed to reactive to make smarter models in the future. And this goes all back to a database that is easily accessed by anybody anywhere, is to understand like what kind of results did we have before. Here are some examples of the comparison of the measurement data at the top left, and then the FEA data at the bottom, and then the comparison right in the middle of the page over there on the right side. This is an actual physical comparison between the two. So you can see this is in logarithmic or true strain values. You can put this in technical strain if that's the data that was given to you. But to understand what are the two data sets, how do they compare? And that way you can feed this back either to the simulation group or to the tool maker to say, you know what, we didn't make these adjustments, but actual hard numbers. Similarly, you can see here, this is the material thickness differences, same concept. Measure data, FEA data, and what the differences are to see how we matching up. Is the tool doing what it's supposed to do? Having the ability to know this knowledge is very crucial to make right decisions. Where tool makers have seen this in their head for many, many years, you can now give them a picture and show them exactly the areas that are having problems. Now, interestingly enough, it's not only just the draw station that you can do. You can track this, as I mentioned, through any station. And in this case here, this is the final part or after the trimming process. Measure data, FEA data, and the comparison between the two. So does the part continue to follow through and do exactly what it's supposed to do for every station? This is imperative to understand because it might be safe out of the draw, but failing in the restrike. You need to know that. So the OFA offers that ability to know that and keep that as a trackable metric so for future runs. And here's a great example of understanding the measured data to the FEA and the comparison between the two, and understanding that you have too much material, or what the friction between having beads or no beads, or the access to the beads, what effect does that have on the part itself. So these are the geometric boundaries where you can actually save material or make adjustments properly, as we mentioned. And here's a great example of those beads that I mentioned, where the measurement data had the beads, the FEA did not, and you can see the comparison difference of where that tension is and the percentage of, I believe it's major strain in this situation, the differences between the two, and that this can be fed right back to the tool floor and say, this is what's actually happening. So in the method of tool optimization, this is something that we see on a daily basis of being used in a very quick form using OFA. Is you might have a hotspot that you want to attack quickly, and you see the red spot before the tool optimization and how it relates to the forming limit diagram on the far right. You have red points above the line, and once you click on those points, it'll tell you how far out it is, where the tool maker can then fix it, re-etch a panel, or have one waiting in the wings, run it again after the fix, and you can now see that the panel is safe. This takes minutes to check these areas and be able to move forward. So having this ability to understand like what direction things are moving, how far above it, so you're not wasting time going overboard trying to fix a small problem. And as I mentioned, the whole process stability side is you can measure the first panel, the 20th, the 200th panel, whatever it is, through the run and make sure that the part is tracking throughout a specific production run, or keep it through a different run and keep these metrics and check these Argus, or I say OFA to OFA. Argus is our unit, I apologize. OFA to OFA, major strain, minor strain, thickness reduction, how it's tracking with each run to make sure that your tool maintenance is tracking well, and making sure that you have that metric, and then kicking that back to a database to make sure that you have those check marks to say that every run is running good, there's no problems, or if there's any problems that are tracking, what are they, and you can make sure that you set those tolerances to say, you know, we need to fix something. So having that internet of this information available to anyone is key. And this is just another example of before trimming process and after the trimming process, where that critical area was, and then where it is not anymore because it was released during the trimming process. So going into this whole process of optical forming analysis, there's an automated version where you saw the manual version of a gentleman taking pictures at different heights. It can now be automated into a box or a robotic cell where the same thing can happen, but now the robot can be programmed one time for the path that it's going to take to shoot the panel, and then brought up any subsequent time after that to run that same pattern over and over and over again for any other parts like that, whether it's a body side, a fender, a hood, whatever it is, placed on a very easy fixture, and the robot can move around, take the pictures, and then automatically do the computations, which now again becomes that set it and forget it mentality that we discussed, where the user can then just bring up the pattern, hit a button, walk away, get other things prepped and ready to go, or maybe do the OFA laser etching, and then two things are running autonomously on the side, and they're just monitoring what's going on. This video kind of shows the automated OFA process in action, as you see the robotic table moving and taking the images and then changing angles and then taking all the positions that are needed to be done. And again, very simple setup, put it right back on the table, bring up the program and run it, and you see the result on the right. The cost cutting time on this was roughly took, it took this down to maybe about, I think 15 or 20 minutes. That would have probably taken you more than an hour to shoot this on the manual side. So again, here's another cost savings slide here of what we can see of implementing a process like this to your daily applications of what it offers here. But the nuts and bolts are that it leads down to the last couple of bullet points, where it's more accurate, less downtime and splits for understanding the full parts response to the forming stations, and then being able to make the right decisions moving forward at a lower cost with less resources. And then the connectivity to the whole thing of Industry 4.0 is that you're just going to have better computer models to make better parts, more proactive than reactive, better design on parts, do things more the first time as opposed to different iterations, because you can see what's happening in real time as you go through. But again, that's the connection here. But all this information is being put into a central database that can be brought up anytime, and really understanding what's been happening. And this kind of brings together how it fits into Industry 4.0, which is exactly what I just mentioned, of that any comparisons that you do to FEA, to CAD models, to previous forming conditions can all be used as a full field state, whether you do it manually or automated on the right here. The benefits are pretty evident, and understanding that and keeping those as trackable metrics as we move forward is crucial. And the last bit of our presentation here, where we're using our DIC for press deflection and understanding the press's performance during the operation. The principle here for the setup is that we're using precision sticker targets, stereo image DIC system, and we're calibrating a larger field of view, similar to what we have for our incoming material side of using DIC. We're using the same system, just on a larger scale, to measure what a tool is doing in production. And here's a nice video of showing you just that, where we can see a press going to bottom dead center, and we're using that as our zero. And notice that the bottom press is not moving at all, because we're able to use the to set our zero state and say, what are we measuring everything to, whether it's global motion or just something in the screen, really understanding how the press is moving during the operation of the whether it's draw station, restrike, or whatever. Same here, this is just a different type of press. You can see the little hiccup in the middle. We can use higher frame rate, slower frame rate, depending on what the application is and what we're going for. But really understanding on a larger scale what the tool is doing. And the cool thing about this is that we can set tolerances within the software, within the DIC software, to report back in real time to say that the tolerance band of this particular press and this particular part is running a little high. It can send an alarm back and say someone needs to take a look at this. Maybe something's gotten out of whack, the gibs are off or something. Very, very easy to monitor by using these systems in real time, or just to really solve a problem moving forward. But understanding what the actual press is doing during the operation in any station is very key. So again, we're measuring the relative displacement of the press in the tool. We can compare it to a baseline, run it dry without anything in it. So it's, again, to understand the press's performance, station to station, how materials affect it, from different materials, from like high strength to ultra high strength materials, and recording the die recipe to track it as an ongoing metric to say, what did we run, not only the tonnages, the type of lube, whatever, throughout the life cycle of the part, as it was colder, as it got hotter, you know, as you're at the end of the run, things like that. But really understanding that will get down to the cost savings of preventative maintenance and understanding any press issues or tool issues, and rapidly be able to solve these problems before your press goes down, which time is money in that case. But these technologies put together can offer such a great solution. But the one thing that we were really proud of being able to do was link this back to a real-time monitoring, where we can actually put that tolerance band in there to set those alarms, where as the press is running, really understand, like, once you're outside that tolerance band, you can have an alarm go off and send somebody in to fix it during the run, to really understand what's going on, and then move on, but be able to fix those problems, because sometimes you do see that, you know, the material is good, the forming is good, everything else is really great, but it's still failing, and that's due to the press itself. Maybe it's just out of whack a little bit. So being able to monitor that is just a huge benefit there. So in a quick conclusion here, to understand that, you know, we talked about 4 different things here in this presentation, starting with the DIC for material properties, going into the OFA patterning for the sheet metal formability and OFA measurements in general, and then DIC for press deflection, putting all these together into a database and having this information of, you know, if your formability is bad, what did the incoming material perform like during the Nakajima test or the bulge testing or even the tensile test? Was there even one done? Being able to know every step of the process, while getting the most automated, accurate data, and being able to take this data and using it productively to make these decisions is proven to be a good asset in every manufacturing avenue. So with that, I want to say thank you. Again, we are Trillion Quality Systems. We have offices in 4 different locations. We'd be happy to answer any of your questions. So with that, again, my name is Yanni Psilopoulos from Trillion Quality Systems, and we look forward to some questions. Thank you.